Hi, everyone. Welcome to our last big chunk of material, the thermodynamics material. We're starting our work in chapters 17, 18, 19, and 20, and that's going to be our story for the next few weeks as we finish things out. Um, I am reminding you that there's a quiz this week on the day when we would normally have had class, either Monday or Tuesday, respectively. Uh, it'll work like the midterm. You've got all day to engage with it, but once you do, it'll be timed. Like the midterm, there will be one question that in which the actual document lives, your solutions, your work, all the everything you develop in solving the quiz should be uploaded to that one question as one submission. Make sure don't accidentally navigate away from that question because it'll think that you didn't mean to submit to it. And make sure that what you're uploading is the one thing that the big pile of stuff that you want to send. A zip file is one way to do that. If you have a bunch of images, compress them, send the one compressed thing. Or if you have a bunch of images, dump them all in a Word document so that I can see them all, and then send the Word document that way. Any problems, let me know. But that's the story. This week we have it's actually relatively straightforward. This week we've got a worksheet and a recitation and a lab. So without further ado, let's start chapter 17. I'm going to divide things into pieces. Roughly, I think we can fit chapter 17 all in one chunk. Maybe not. Maybe it'll make more sense to cut it into a few pieces. But this week we're going to have a fair amount of content uploaded. 17, 18, 19, and 20 there's a lot in those 4 chapters. So we'll do what we can. Okay. I've got an image to show you in a second, but first, I'd like you to think about some of the work that we've done in the course up till now. We started talking about motion. How does a thing move, and what makes it move? And then, all right, so what are the things affecting its motion once it is moving? And we considered some other kinds of motion along the way using the equipment we developed. We talked about rotation, we talked about oscillation, and fluids. And I'd like to put all of that together. I'd like to, way back at the beginning of the semester, we talked about the fact that the thing we'd like to do is to conceive of a machine that would do motion for us. That was the very first thing we talked about after we talked about the syllabus, that as humans in the world, we need to get from point A to point B, and we'd like to do it faster than walking. So there's some sort of machine that we're going to develop to do this, to exert a force on our person and cause us to move. And there's some question, I think, about what the best kind of machine is to do this. But now that we have fluids, now that we've talked about chapter 12, we can talk about a system of a fluid system that we can bring with us, right? Let's strap it to this machine that's taking us from one place to the other. Instead of like a water wheel or something like that, where we got to stay there where the water is, and we're not going to be able to you know move. Um, so the goal, at least in this configuration, is to design some sort of system so that a fluid system so that the fluid is capable of doing work in order to move us, in order to change our kinetic energy from resting to moving. And we'd like it to be, well, I mean, I guess if we're making a wish list, I'd like it to be repeatable. In other words, I don't want to have to like set up the whole thing and then press the button and say go, and then once it's all fall down, I don't get to move anymore, right? Like it shouldn't expire that way. It should just repeat over and over again, because I might need to go farther than I originally designed the machine, right? So, if we just bang, the fluid system does a thing and we go as far as we go, and once we coast to a stop, we're done. That's not a very good machine. So we're looking for a thing that's repeatable. So when we say repeatable, I think rotation and periodicity, right? Something repeatable every so often. And fluids, and I mean, we're I think preconditioned to think that putting some sort of platform on round objects such that we can roll instead of slide, right? So that we're not dealing with sliding kinetic friction, but we're dealing with rolling friction, which is much nicer. So if we've got round things that are rolling, we're trying to create rotation in the wheels with a periodic system that runs on a fluid. We want an engine. This is a figure from chapter 20. And it's a way of me signaling where we're going to go. And so now the question is, how are we going to get there? This is the thing that I'd like our machine to do. There's a crankshaft that is related to the axle on which the wheels are mounted, and we need that to rotate. All right, so we can attach to it the connecting rod, and we can push down on that piston or up, and the connection to the crankshaft will rotate around as the piston moves, causing the crankshaft to rotate. And it's the mixture in the chamber inside this cylinder that is going to be doing the thing, doing the work, I guess. And it's step 4 that I'm really interested in here, the power stroke, where the mixture expands for some reason, pushing the piston down, moving that connecting rod and the connection to the crankshaft, causing the crankshaft to rotate. So our large question for the next 4 chapters: how good is this machine? A, does it work? B, why does it work? C, can we make it better? I don't want to spend any more mixture, any more fuel than I need to get from point A to point B. Is this the best way to do it? How good is best, right? Like, what kind of, if we have to put some, if we have to make some investment of energy, how much of a return on that investment are we going to get? How much work output is this machine going to do every cycle, I suppose, compared to how much, energy we had to put in to get everything ready? Is there a maximum, right? Like, can something be 110% efficient, right? We get more out than we put in. Or can it be 100% efficient? Or, is there some lower number? Like, is there a maximum less than perfect efficiency that we can achieve? Um, these are my questions for the next 4 chapters. And the place we're going to start here in chapter 17 is with the word hot. In the power stroke, hot mixture expands. What does hot mean? Hot is a problem. Okay, so hot or cold, so it's attached to our idea of temperature. As humans, the deal with hot, right, is that it feels hot, right? If we touch a hot stove, well, if we touch a if we touch a hot stove, it feels hot. So what does that mean, really? How do we science with the idea that something feels a particular way, that we'd like to be numeric and quantitative about our felt experience, right? It's not so much an objective observation, right? Like, if we get a ruler out and measure the length of this whiteboard, it is what it is, right? Like, and we all can hold the ruler up and agree that that's a thing. But if each of us put our hand on the whiteboard, some of us might say, oh, it feels, it's cool to the touch. And some of us might say, well, no, it's room temperature. Or some of us might say that it's warm in this room or that it's cold in this room. So how do we agree on the conversation we're having about how it feels? What is hotness and what is coldness? And that's the definition we have for temperature. And I think back when we defined Newton's second law, I said that a force defined as a push or a pull is my second least favorite definition. Temperature defined as hotness or coldness is, I think, my least favorite definition that we're going to bump into. At first, that's all we have. That's the thing. Later, in another chapter even, we can be a little bit more precise about what we mean when we say temperature. But for now, it's hotness or coldness. So we'd like to measure that. And the ways, so we start looking around for physical, observable things like the length of this whiteboard that change as what we perceive as temperature, hotness or coldness, changes around us. So we're in a hot environment and we're looking at a thing, and then we take that thing to a cold environment and we see if it changes. We need a way to be quantitative, to measure the change in whatever property it is of that object, whether it's the space that it takes up, or it's electrical resistance, resistance to the flow of electricity, or whether it's the pressure that a gas exerts on the walls of a container. And here's a couple examples of the first one, especially of a familiar thermometer, a way to meter what is hot or thermal. Changes in temperature cause the volume of the liquid to change. And so as the liquid's temperature changes, increases, its level rises in the tube, a volume thermometer. The figure B is an example of a constant volume gas thermometer. As the temperature of that gas increases, its pressure increases. And there's nothing fundamental about those things. We just looked around for a while until we found something that behaved differently at different hotnesses. There are other examples of thermometers that we could think of, but for now, let's just think of these. The trouble with our glass tube thermometer with the liquid inside, where if we change the temperature, the volume of the liquid changes. It's familiar to us by now, but the trouble with it is that I still don't know how we measure the temperature of a different thing, right? So if the liquid expands, we know that the temperature of the liquid is higher. I'm still not really sure what the values are for that, but we know that if the temperature that a temperature increase results in a volume increase. But that's a temperature increase of the liquid. What does that have to do with the surroundings? Like, how do I use one of these thermometers to measure the temperature of the air in this room as opposed to the liquid in the thermometer? Well, okay. Imagine we've got a thing of coffee or a cold beverage and a thermometer. And we stick the thermometer in the beverage, and at first, the thermometer is at room temperature. Fine. So we know from experience that when we expose the thermometer to the environment at a different temperature, the soda in the cup, for example, that the level of the liquid in the tube decreases because the iced soda is colder. That the level in the thermometer decreases until it doesn't decrease anymore, until like whatever was causing it to decrease and whatever resistance it has to the decrease are in equal opposition to each other, equilibrium. It's like the level of the liquid in the tube is in equilibrium. It's not increasing and it's not decreasing anymore. It's stable. And that's what we decided to define thermal equilibrium as. That if two things are at the same temperature, then we have said, yes, those two things are in thermal equilibrium with each other. And it's another way to say, okay, well, the thermometer and the soda are in thermal equilibrium with each other. The volume of the liquid in the thermometer isn't changing. It's in equilibrium. And this thing is a thermometer. So I'm reporting thermal equilibrium. And let's define that to be the case that is thermal equilibrium. When two objects have the same temperature, thermal equilibrium. So if two objects reach a thermal equilibrium, in other words, the level of the liquid in the tube isn't changing, then we know that they are at the same temperature. The laws and results of thermodynamics were published before anyone realized how important it was to define what it means to be in thermal equilibrium. Same temperature. It's not. It doesn't have to be that way. We could say that the two pieces, the two components of the system, need to have the same total energy or something. But we could define thermal equilibrium as something else. We don't have to define it as the same temperature. It was after they published the first, second, and third laws of thermodynamics that they realized that they had been defining it the way we're talking about all along. That thermal equilibrium means same temperature. If you look up the 0th law of thermodynamics, it's actually called that because they published 1, 2, and 3. So they had, it comes before that. It's the 0th law. But if you look up, and even in our textbook, it tells us that the 0th law of thermodynamics is this thing. And that if two systems, A and B, are each independently in thermal equilibrium with some third system, C, then they are both in equilibrium with each other, which doesn't sound like much of anything to me. It sounds like the transitive property. Like I don't really get as a law. It just seems like a thing that ought to be true. But the fact that we define thermal equilibrium as the state of having the same temperature, that's important. That's the big, in my opinion, that's the big news for the 0th law. Let me just peek and see what's coming up. Okay. So if we're going to, I gotta stop sharing the thing here for a second. Okay. If we're going to define a temperature scale, we need to pick, right, because that's the thing. We got to make markings on our thermometer so that we know what temperature it is when the level of the liquid has expanded to this particular, height in the tube. So I can't just mark it whatever. Because if I hand it to somebody else and they walk down the street, they're going to have no idea what those markings mean. So the idea is that we should compare it to things, events that always happen at the same temperature everywhere, no matter where we look. And the very common one is freezing and boiling points. And you know where I'm headed now, I think. That the boiling point of water and the freezing point of water are two things that happen. Water's freezing. I feel that it's about the same temperature. So I'm going to use that as my benchmark. If water's boiling, it feels to me about the same temperature. So let's use that and let's agree on a temperature scale. What do you want to call the freezing point? Let's call it, I don't know, 0 degrees. It's the bottom. And the boiling point, let's call it 100 degrees. I like metric stuff, right? Powers of 10. And yeah, we know that this is the Celsius temperature scale, or the centigrade, because there are 100 gradations between freezing and boiling. Centigradation. Other temperature scales that we are, in the U.S. familiar with, we can talk about 32 degrees for the boiling or freezing point, and 212 for the boiling point, and that's the Fahrenheit. Fahrenheit scale, absolutely. Okay, what if we don't have one of those temperatures? How do we get from one to the other? Well, it's not hard. We could make ourselves a relationship. We've got 2 points, Celsius, Fahrenheit, 100, 212, and 0, 32, and 2 points determine a line. So from this information, we could figure out the equation of the relationship between Celsius and Fahrenheit, the equation of a line. In other words, let's say from Fahrenheit to Celsius. Yeah, you know what? Let's do it the other way. From Celsius to Fahrenheit. We've got 32 degrees is 0, and 212 is 100. And there's a relationship there between Celsius and Fahrenheit. Okay, in order to find that, we need the slope and we need the intercept. So what's the slope? The slope should be rise over run. So it's the change in the Fahrenheit from 212 to 32, and the run is the change in the Celsius from 100 to 0. So it's 180 over 100, or 1.8, or 9/5. So the slope should be 9/5, and we can see the y-intercept just from here. So we know the relationship between Fahrenheit and Celsius is to multiply the Celsius by 9/5 and add 32. So of course we know now too that the opposite relationship, we gotta subtract the 32, and instead of multiplying, we divide. So now we can get from Celsius to Fahrenheit and back. Is that right? This trick works a lot better in person. And the answer is no, this isn't right. We subtract 32, and then we have to divide both sides of the equation. So we're going to multiply the whole thing by 5 minutes. Could we, if we wanted to, make up a third scale, that has to do with boiling points of water? Sure. Could we use a different subject? Talk about the freezing and boiling points of, I don't know, boron? Why not? And we would develop the equivalences exactly the same way. 2 points determine a line. We just need to know what that new scale is compared to one of these, and then we've got the whole story. Okay. You might already know that there's a scale missing. And it's this one. Well, it's related to this one. As we started to do experiments with our constant volume thermometers, the one in the, that I showed you a cartoon of earlier, we can make a plot of the pressure that we observe as we increase the temperature. And no matter what we did, the pressure increased as the temperature increased. But if we use different substances inside this canister, then those lines have a different intercept, right? If we're using, hydrogen, oxygen, nitrogen, we get different intercepts on this curve, but they all increase, right? If we extrapolate backwards, those Curves all look like they have the same x-intercept, that there's one temperature at which the pressure, no matter what it is zero. Now, we can talk about what that actually means. You know, is it actually a zero pressure, or is it like a minimum possible pressure or something like that? We're tripping into quantum regions, uh, but it certainly looks like there's a point. If we extend all the graphs back, it looks like there's a point at which all of the pressures are zero, no matter what the thing is. And I'm going to point to the temperature scale behind me. No matter whether we're using water or hydrogen or oxygen or what, it's not that we're marking 100, cents between the freezing and boiling points of water. We've got zero pressure no matter what it is. You know, it's not relative to water, it's not relative to boron, it's not relative to any other thing. It's just true for everything. So it's not relative, it's the opposite. It's absolute. It's the point, the temperature at which there is zero pressure, absolutely, not in relation to anything else. So we'll call it absolute zero. And let's define a new scale that puts zero at absolute zero. But let's keep the same spacing as centigrade, because I like the metric thing. So we can define the other temperature scale, and the one that we'll use a lot, Kelvin, not degrees Kelvin, because degrees of change relative to something, this is just boom. It's not relative to anything, it's just Kelvin. Okay, how do we get the temperature to change? So we can see a picture here. We've put the constant volume gas thermometer in a bath of ice, it looks like. We could also, sorry, hold on. We could also expose it to flame. We could directly heat the thing. You know what? I don't want to talk about this yet. I want to go back. So we're here. There's you know what? Let's cut it here just for